All right, welcome to the third KCS talk this semester. Our speaker today is Dr. G. Dr. G, all right? The title is long, but no, the purpose is very simple, to give new tools and insight for the multi-objective optimization problem in machine learning applications. Okay. So let's welcome Dr. Joe for his exciting talk. Okay. Okay. Let's give him
Thank you for the warm introduction. Welcome to my talk. And in today's talk, I will briefly talk about our recent research on this topic, multi-objective optimization, and I will cover two parts. One is on the exact Pareto fronts in MDP, and another is the efficient gradient descent methods. Maybe there are some terminology here in the title that you are not familiar with, but don't worry, I will cover those later. Okay, so first let's see some very simple concept here. So what is optimization? Optimization is the process of finding the best solution to a problem under given constraints. It is fundamental to decision making of the engineering science and of course artificial intelligence. For example, let's see this function. Right? So you can see the function can be drawn as a curve, and if we want to find the maximum of this function, then this can be regarded as a very simple optimization process. I would say optimization is simple, optimization is everywhere in machine learning and AI. There are some real-world examples that also use optimization techniques. So let's see a very simple scenario that if we consider a company sells product and its profit depends on the selling price. And when the price is low, sell more units, but little profit per unit. When the price is high, sell fewer units, but we have high profit per unit. And of course, the problem is that we want to find the optimal price that can maximize the total profit. So that's can be modeled as an optimization problem. So you have some relationship, you have some constraints, and you want to find the optimal thing to maximize your objective. And if we write it as an optimization problem formally, then we use some notation like here. So price is denoted by X, demand is 200 minus 5 times X, and the cost per product is 20. Then the profit can be calculated in this like quadratic function. So it's 5 times x minus 20 times 40 minus x. I think we can easily calculate the optimal solution to maximize the profit, and the optimal choice will be x star equal to 30, which means the best price to maximize the profit is 30. Then let's consider one question. So if the profit isn't the only concern in our previous example, I mean, of course, the profit is always the first objective for any company, but sometimes we or the company or the businesses don't optimize the profit alone, and other objectives may also matter, which leads to our today's topic, multi-objective optimization. For example, we can view the customer satisfaction as a secondary objective or as another objective. That means, and if we are considering the customer satisfaction, then we have some relationship with the price. So high price hurt the customer satisfaction, and we actually want both high profit and high customer satisfaction. So if we write it down, then indeed we have two quantities that we want to maximize: profit and satisfaction. And here we just use a very simple like linear function to denote the satisfaction with respect to the price. So it's 100 minus x. And then we have a very natural question, a follow-up question, that is, what's the meaning of maximize a vector? Right? I mean, we know it's very straightforward to maximize a scalar because the scalar is comparable. So one scalar is larger than another scalar. But if we are maximizing multiple objectives and maximizing a vector, then the meaning of the maximize may be not that straightforward.
I'm sorry, I have a question here.
Sure.
Now, when you have several objectives, do you put weights on those different objectives?
Yes, I think that's a very good observation, and I will talk that strategy later. And that's indeed a very, I would say that's a very straightforward idea to solve this multi-objective optimization. And and the short answer is yes. Usually we have the weights. Okay, so then let's see more details about this problem. So when we deal the problem with multi-objectives, we must consider them simultaneously, and we have to first define what's the best solution for this multi-objective optimization, or in short, MO. And actually, it's hard. I mean, there is no unique best answer out there to say that one solution is better than the other. So it's hard to define such single most ideal solution because someone has someone prefers this objective better than the other, while the other people may have different opinions. So it's hard to define a single most ideal solution. Because it depends on the importance of each objective, and that may be undefined. However, we can think this in the other direction, that we can easily identify solutions that are not desirable, which means those undesirable solutions has the following situation, that every objective can be improved simultaneously. So if a solution satisfies this description, then of course this solution is not desirable because every objective can be improved simultaneously. Right? So then that's not ideal or not desirable. And that actually leads to the very important concept in this multi-objective optimization, which is called Pareto optimality. So the Pareto optimality says that a solution is Pareto optimal if no other solution improves one objective without worsening at least one other. Right? So that just means for those Pareto optimal solution, we know that this solution is not belong to the undesirable situation. That means if we want to increase one objective, we have to sacrifice other objectives. So those solutions belongs to this Pareto optimal solutions. And I would say maybe the main goal or the main purpose of solving a multi-objective optimization is to find a suitable Pareto optimal solution, right? Because we know all the ideal solution must be a Pareto optimal solution because that's kind of the minimum requirement of a desired solution. And of course, not every Pareto optimal solution is what we want because sometimes we want because sometimes we have certain preference on certain objectives. We may have some weights on those objectives. So I would say not every Pareto optimal solution is ideal, but at least every ideal solution should be Pareto optimal. And go back to our previous example, then we can actually draw all the Pareto optimal solutions. And we use the terminology Pareto front to denote the set of all Pareto optimal solutions in this multi-objective optimization problem. So in fact, if we check those relationships, and then you can see in this figure, this like shadowed area corresponds to the Pareto front. So this red line denotes customer satisfaction, which is a linear relationship, and then the blue is a quadratic relationship of the profit. So if we apply the definition of the Pareto optimal or Pareto optimality to this situation, we can see only in this part belongs to the Pareto optimal point, because you can see when the price is less than 30, then you have to sacrifice one objective to increase the other objectives. So that's the part corresponds to the Pareto optimal. And we actually call the set of all Pareto optimal solutions as the Pareto front, because that's kind of as a front, right? It's a surface of something. Okay, then of course I have talked a lot about the optimization, and I want to emphasize the optimization is indeed a very important part in almost every method in the machine learning. So for example, the machine learning usually needs some training process, and in the training process we will using some methods like a gradient descent to minimize the loss function. And you can see this minimized loss function is indeed a typical optimization problem. So I would say the optimization is indeed an essential part of every machine learning method. And for this multi-objective optimization, it also plays an important role in the machine learning when we deal with multiple requirements. If we just want to minimize one loss function or want to achieve one requirement, then the single objective optimization will be enough. But sometimes we want the machine learning to achieve multiple requirements. Then, of course, we need to turn the single objective optimization into this multi-objective optimization. So that's why we need to study some techniques or some methods in the multi-objective optimization. And actually, I can give some more concrete examples. For example, this multimodal learning. Right? I mean, multimodal learning is indeed a very hot topic nowadays, which means the machine learning model can take multiple, can deal with multiple inputs or multiple types of the task. For example, the text, the image, audio, video, they can be the input of one single machine learning model and give certain outputs based on different types of the input. And of course, you can see here, different inputs need to be solved or can need to be formulated differently, and then this multi-objective optimization is closely related to this multimodal learning. So that's one application scenario that why or how the MOO is related to the machine learning. And another example is the multitask learning. So multitask learning, just like the name, right? It handles multiple related tasks. I mean, there are different categories, for example, continual learning, transfer learning. They all belong to this multitask learning. And in those multitask learning, we usually need to satisfy, or usually we have multiple objectives. For example, in the continual learning, we want to minimize the forgetting of those knowledge and maximize the current accuracy or the accuracy of the current task. So because we deal with multiple tasks, there are usually multiple objectives. So that's why MOO also can be important, can be helpful to solve those multitask learning. And some other application of MOO is learning with privacy, fairness, or other requirements. So in many of real-world applications, optimization only for accuracy can lead to undesirable outcomes. For example, if some application needs privacy, then we have to ensure the models do not leak sensitive information. Some examples like this differential private machine learning that consider the accuracy and the privacy at the same time. Some other types or some other machine learning consider the fairness, which want to avoid biased or discriminatory predictions. Some terminology like this fairness, where machine learning actually consider or actually balance between the accuracy and the fairness constraints. Of course, there are some maybe there are some other types of the machine learning that not only consider the accuracy but others. But privacy and fairness may be the two majority ones. And in the multi-objective optimization, you can actually write different objectives, and we actually want to maximize those objectives at the same time. So that's how the MOO is related to those privacy and fairness study in the machine learning field. Okay, I think that's a relatively long introduction, but I want to give a very clear background of the MOO and how the MOO is related to the machine learning field. And in today's talk, I actually talk about our two recent research. So one is about how to find exact trade-off front for the multi-objective MDPs, and another is efficient multi-gradient descent to solve this multi-objective optimization. So the first work is actually is a collaborative work with researchers at the OSU and with Ohio State University, and it is recently accepted by ICLR 25 and actually got a spotlight presentation. Okay, so I also need to give some more background on the reinforcement learning and MDP. So reinforcement learning is indeed a framework for sequential decision making where an agent learns by interacting with the environment to maximize the cumulative reward. Right? So that's the reinforcement learning. I think that maybe many of you have already know some information about the reinforcement learning, so I won't spend too much time here. And the MDP, or Markov decision process, is indeed the very important concept behind the reinforcement learning. So it is usually defined with some parameters. S denotes the set of the states, A denotes the set of the actions, P is a transition kernel or transition probability function, which denotes the probability of reaching state S prime from S after action A. And of course we have the reward function, which tells how much reward we get when we do action A at the state S. So that's a scalar value. So that's a reward function. And sometimes we also have this discount factor gamma, which is a parameter between 0 and 1, that determines the importance of the future rewards, because it's usually better to get a reward at the current time than get the same reward in the future, because those rewards get discounted when the time passes. Okay, so when we talk about the reinforcement learning or MDP, we also want the purpose is to solve some policy to maximize the long-term return. And the policy, the definition of a policy pi is a rule that defines an action selection in an MDP. Right? Very simple definition. And there are two categories regarding the policy in MDPs. So the deterministic policy means that we describe, or the policy can be described in a deterministic manner. Right? So that means when we reach a state, we will do a single action with 100% probability. So that's a deterministic policy. So you can we use this equation to know this. So the pi take the input s and the output will be an action. So that's a deterministic policy. And in contrast, the stochastic policy means the policy actually described by a probability distribution over different actions. So you can see even state s doing different actions is described by a probability distribution. So that's not deterministic, that's indeed stochastic policy. And then I also need to talk about what the meaning of this multi-objective MDP. In fact, there is only one slight difference when we compare the multi-objective MDP with the traditional single-objective MDP, which is the reward function. Because all the other things are the same, the state space, action space, probability distribution, or transition probability, discount factor, they are all the same. But the reward is the only difference, because when we consider multi-objective, that means we have multiple reward functions for each of the objectives. Right? So then you can see there is an additional dimension in this reward. So in a single objective reward function, the reward function is s times a dimension, but here, since we have d different objectives, so it has additional dimension in this reward function. Or in fact, it's a reward tensor. Right? It's no longer a matrix, it's a tensor. And the long-term return is here, right? So I mean, this equation is very similar to the traditional single objective MDP, but here, since the reward is a vector for different objectives, and the overall long-term return will also be a vector. And then if we want to solve the Pareto front in this multi-objective MDP, then we have we need a certain way to solve it. Right? I mean, we know how to solve a single objective MDP. We can use we can use many methods. For example, those value iteration, policy iteration. Those are methods written in the textbook of those reinforcement learning. But if we are talking about multi-objective MDP, then if we want to use those traditional methods to solve it or to get some Pareto optimal point, then we have to do certain changes or certain pre-processing to turn those multi-objective MDP into one or into a single objective MDP. Then we can use those methods to solve a solution. So that's the preference vector comes into play. The preference vector actually means what's the weight of different objectives. Right? And if we know such preference vector W, then what we do is that we just apply this W on the reward function then we can formulate an equivalent single objective reward function. And then we can solve this single objective MDP by using any existing method. So you can see eventually if we are given a preference vector, then what we do is that we maximize this weighted sum of each objective's long-term return. And it is equivalent to solve a single objective MDP using the reward function, which is a weighted sum of those individual reward functions for each objective.
I have a question here.
Yes.
Sorry. That RD means three-dimensional for any dimensional space, right?
Yes.
And WI, RWI non-negative?
Right. So this is
All right. So are you talking about maximizing or minimizing this on a unit square?
Yeah. I mean, of course, it's weighted. It's a weight, right? I mean, we let this weight equal to 0, but the sum of the weights equal to 1 means that we want to normalize the weights.
So this is something like unit sphere?
I don't think this is a sphere, because if you are talking about a sphere, then it should be the norm of this vector is equal to 1. But here, this is the summation of it. This is more like a distribution. Sphere means that the norm of the vector is equal to 1.
All right.
Anyway, it can be shown that this solution must be a point on the Pareto front, because those non-negative weights, and then if you can maximize this, and if you check the derivative or check the slightly difference, then you can see it can easily prove that this solution must be a point on the Pareto front. So that means if we get a solution of this optimization problem, then it corresponds to a Pareto optimal point, or corresponds to a point on the Pareto optimal for the original multi-objective optimization. And if we already have that method, then why we want to investigate the Pareto front further, right? I mean, we already, if we are given the preference vector, then solve that single objective MDP, then we are done. Then why we need the Pareto front? In fact, I would say the Pareto front will be very useful in some scenarios. So if we don't know the whole Pareto front, then when we want a solution, we have to do the following steps. The first step is that we set a preference vector, and we get a Pareto optimal point by solving the single objective MDP. I think that's not difficult. However, after we solve it, when we look at those solutions, we may face some possibilities. One possibility is that we are satisfied with it, then it's done. I mean, we finish the job. But usually that doesn't happen. The ideal situation doesn't happen very frequently. And most of the cases, we are not satisfied with it. For example, we want some objective to be a little bit higher. For example, if we consider the previous example about the profit and the customer satisfaction, after we solve it, we look at the number of the profit and customer satisfaction, and we think maybe the profit is a little bit lower, and I want to increase the profit a little bit more, and I can afford the decrease of the customer satisfaction a little bit. Right, so I want some small adjustment on the outcome. So if that happens, then I would say that usually happens. That happens frequently. Then we have to calibrate the preference vector and solve this MDP again, and hope the result satisfy our original expectation. Calibrating the preference vector means that we can make the weight for that specific objective a little bit higher while tune down the other weights a little bit. But how far or how much we should increase the weight of one objective is actually uncontrollable, and we actually cannot predict the outcome before we solve it. And so that's indeed very unpredictable or uncontrollable method to calibrate the preference vector to satisfy those small changes. However, in contrast, if we know the whole Pareto front, that means we have the whole set of all the Pareto optimal points. Then what we do is that we just move the current point towards that direction. For example, if we want the objective 1 a little bit higher, since we already know the whole Pareto front, we just move this point on the Pareto front to a certain distance. So then we can easily control how far we go and how much we sacrifice the other objective. So that means if we know the Pareto front, then we have a more precise way to choose the solution that we want. So that's the intuition behind it, why we want the Pareto front. Okay, so and that actually means there are some challenges of those previous preference vector approach, because the preference vector approach is not designed to solve the whole Pareto front, right? It's just designed to solve one instance or one point in the Pareto front. And as I just said, it's sensitive to the scales of the objectives, which means if you scale one objective by 2 times, 3 times, then the change or the tuning of this weight vector will be scaled as well, so you cannot control precisely. So that's why I said it's sensitive to the scale of the objectives. And of course, it struggles to adapt to changing preference. So if your preference changes, then you have to solve the MDP again, which take time. And the critical problem is that if we want to get the picture of the Pareto front using this preference vector approach, we have to scan or traverse this continuous preference vector space to approximate the Pareto front. That means we can never get a precise Pareto front. It's only approximation because it needs to traverse a continuous preference vector space. The preference vector is continuous. Okay, and then in our work, we actually propose a different approach that can solve this problem. Or I would say this is the first algorithm that can give you the precise Pareto front, not approximation. It's a precise description. What we use is some geometric characteristics of the Pareto front in the MDP. For example, this Pareto front lies on the boundary of a convex polytope with its vertices corresponding to the deterministic policies. Any neighboring policies on this boundary differ only one state action pair. And the benefit is that we only need to solve the MDP once, and we can find the exact Pareto front. It's not approximation. And we show that it's much more efficient compared to some similar algorithm. But those similar algorithms cannot solve the exact Pareto front, but we still listed them as a similar algorithm to compare the efficiency.
So,
yes.
how big is the Pareto front?
What?
Are we talking continuous, or are we talking? Are we looking at a continuous Pareto front or discrete?
Continuous.
Okay.
So we actually solve the continuous Pareto front. Exactly. Oh, by the way, but although it is continuous, since I said it's a convex polytope, that means it can be described by discrete elements. So that's the main behind. Okay, then here is a brief overview of the algorithm. So we have the initialized by solving a single objective MDP with an arbitrarily chosen preference vector. Then we run a loop to actually traverse the surface of this Pareto front. So using those geometric properties. In each iteration, in each loop, first we find those neighbor policies. The neighboring policies means the policy that is only one state action pair different from my current point. And I identify several neighboring policies. Those are deterministic policies. And then I will calculate the incident phases of those neighboring policies on neighboring points. And then I will extract the Pareto front phases from these incident phases constructed constructed in the step 2. In fact, the actual algorithm has some additional steps and has more precise description, but I don't have enough time to come over every line of the pseudocode. But here, these are some rough steps of this algorithm. So first, identify the neighboring points, then construct the phases, and then extract the Pareto front phases out of those phases. And in fact, why that algorithm work actually needs a lot of proof, because it doesn't hold naturally. We have to prove that the Pareto front satisfies certain properties such that we can use those the aforementioned algorithm to find the whole Pareto front. In fact, I list several important theories that we need to tell that algorithm works. So the first is that the set of the whole solution space is a convex polygon, which means although it's a continuous Pareto front, it can be described by discrete elements like the vertices, edges, and then we have this distance 1 property on the boundary, which means it differs by only one state action pair. We also need to prove the sufficiency of traversing over edges. Right? We prove that if we move this one point to another point by one edge, and it is already sufficient to traverse every vertices. That means we have to prove certain properties, like here. So for any vertices on the Pareto front, at least one edge on the Pareto front connects it to another Pareto optimal point. And we to further enhance the complexity or save the time, we also prove the local property of the Pareto front. Because if we talking about visiting the neighbors of one point, that means we have to visit s times a minus 1 neighbors. That's quite inefficient because s times a may be quite large. So when we're visiting the neighbors, we actually use some local property to reduce how many points we need to consider, right? So we also have some theory to prove that we only need to consider those points that is on the surface of the convex hull of those neighbors, right? So that actually much fewer points than the whole neighbor, than the whole set of neighbors. Of course, I cannot go to details, but I just roughly talk about those concepts. So each one sentence here corresponds to a theory that needs pages of the proof. And here, let's see some visualization of this work. So you can see one interesting phenomenon is that the Pareto front is not always consisting of phases. Sometimes it has lower dimension phases. For example, in this 3-dimension Pareto front, we have 3 objectives, right? And then the red parts are the Pareto front. And you can see this is a phase, that's no problem. But here, this edge is also a Pareto from. And if you use some approximation method, then it's highly likely that you will miss the points on this lower dimension Pareto from. So that's also one benefit of our approach, because we find a precise Pareto from, we don't lose any points. So you can see by our algorithm, we actually find this interesting phenomenon for those lower dimension physics can be part of the Pareto from. And a byproduct is that we not only characterize the Pareto optimal policies for those stochastic policies, we also have the deterministic Pareto optimal points policies. But that's just a byproduct. And that's exactly why we can compare our method with some existing method. Because although no algorithm solve the precise Pareto optimal policies for the stochastic domain, but they have some algorithm to solve the deterministic Pareto optimal policies. So since this is our byproduct, we can still compare our algorithm with the existing algorithm to get a deterministic Pareto optimal policy. And this is our comparison. And you can see even if we compare with that aspect, we still save a lot of time compared to the existing algorithm. So that means our algorithm is very efficient. Okay, so I think that's all I want to talk about the first work. And since I don't have too much time left for the next topic, I will roughly or quickly go over the main findings and the main ideas of this work. So it is a periodic stochastic multi-gradient descent for fast multi-objective optimization. So this is a joint work with people at the RIE and OSU. And it is recently accepted by the AAAI 25. Gradient descent, I believe most of you have already know the gradient descent, right? So just means doing a gradient and decrease loss function. And gradient descent in the multi-objective optimization means that we have multiple loss function, and we calculate the gradient of each loss function, right? And then eventually the gradient should be some kind of weighted sum of those individual gradient direction. And there are some concerns here. We wanted to converge fast to Pareto optimal point. And we also want the computation complexity not too high, because we want, when we use the gradient descent, we want the algorithm run fast. And sometimes we also have the requirement of the diversity, which means sometimes, sometimes the algorithm will stop in the local optimal, and if it doesn't have certain diversity or randomness, then it will always stop into one point, right? So that's what I mean here. Diversity sometimes is also needed to escape the local optimal. And there are some existing ways to solve this. One is a linear scalarization, or LS, which is a straightforward idea to solve it. Just given a predefined weight vector, and then we just let the gradient to equal to a weighted sum of this individual's gradient. I think that's a very straightforward idea, and of course it will give us the Pareto one Pareto optimal solution, and it's easy to calculate. However, this has certain problem, because you can see there may exist conflicts among multiple objective gradients, because when you calculate those gradients, sometimes this gradient has an opposite direction with the other, then the gradient will become very small and move slowly. So that's the drawback of this linear scalarization. Yeah, that's what I said, not the fastest way to approach the Pareto optimal point. And there are some further enhancements, which usually called the gradient manipulation. That means people dynamically adjust those weights of the gradient descent direction. So one typical algorithm is called this multiple gradient descent algorithm, or MGDA. So in the MGDA, the people actually solve an optimization problem in every iteration of the gradient to calculate one direction that will descend every objective. So you can see there are some optimization, and we actually solve the pure problem of this optimization. And then after we calculate this direction to decrease every objective, then you can quickly approach the Pareto optimum, because at every iteration, every objective will decrease. Right? There will be no conflict. Let's talk about our motivation. So for the linear scalarization, it has many conflicts. So it's simple, but it may be slow. It may, slow in the convergence speed. And for the MGDA, it's very efficient to quickly approach the Pareto optimal, but it's hard to compute, right? Because in every iteration, we have to solve an optimization problem, so it's slow. And what we want is that we want something in between. Right? We want to mix the advantages of both algorithms. So eventually, it leads to our design that we periodically calculate the best direction. Right? We don't calculate the direction in every iteration. We just recalculate the weights periodically. You can see this line, we actually introduce some interval R. So after R iterations, we calculate or we calibrate this direction, or gradient descent direction. I actually use a very simple function. This is called the Fleming function, which is a typical test function for the multi-objective optimization. This linear scalation will give you only two extreme points, right? Either one objective is maximized or the other. And the MGDA will quickly, you can see, directly approach to the Pareto optimal. So every step, you will go one step closer to the Pareto front. But remember, each step will cost you a lot of time to calculate. And what we do is that since we mix those properties, we only periodically calculate the best direction. You can see this is the trajectory of how our solution approach to the Pareto front. And you can see it also introduces more diversity of the solution. You can see eventually the solution distributed over the whole range of the Pareto front. So this curve denotes the Pareto front of this problem. And also we do some theoretical guarantee. For example, the convergence speed for the strongly convex problem, general convex problem, non-convex problem, we prove the convergence speed. And we also have some numerical experiments. You can see the running time is not as fast as linear scalarization, but we have a much better accuracy, because we do other, like we calculate the best descent direction in certain periods. Okay, so that's all I want to talk today. Thank you all, and I'm happy to answer any questions.
How do you determine R, the period?
Oh, sure. This period, I would say it's depends on your own choice. Currently, we don't have algorithm to tell you the period. I think it depends on, or it varies when the task changes.
So the solution trajectory that you showed was obtained with a single value of R.
Yeah.
Okay. So
because this algorithm or this MGDA calculates the direction that decreases every objective in every iteration. So that means every iteration it will go directly to the Pareto optimum.
yes, I get that. I was talking about your solution in the next slide.
Yes.
Yeah, this one. So, okay, the way R is determined, could it be tied to the number of dimensions D? the dimensions of the problem is somewhat
Well,
high.
it's 2, right? I mean,
Yeah,
because
yeah,
we
yeah,
are
here it is 2.
two.
Here it is 2. But suppose it is large, then yeah, I want to know if like how will it influence the determination of the value R?
Oh, yeah, I think, I mean, we actually just randomly choose the R. I guess in this experiment, the R may equal to 5, which means every 5 iterations, we calculate the direction. So you can see there are some turning points of the direction. So maybe after a few points, and you can see this point, it changes direction going to the Pareto front. That means you actually calculate the direction using the optimization to calculate the best direction.
Okay, thank you.
Dr. Dietz?
Yeah, so I'm just a little bit confused here. So I get that you're trying to figure out what the direction is that you want to move in, but how do you know what step size? I'm used to thinking in terms of things like simulated annealing and things like that.
We don't do any special operations of the step size. I think just set the step size as a fixed constant. I think that's the common choice in those vanilla gradient descent. Just choose the step size and do the gradient descent count. I mean, what we are investigating is the direction of the step size.
Okay.
Any other questions?
So correct me if I'm wrong, a smaller step size would mean more accurate results, but would take much longer. So then the way that you would choose a step size would vary on how much time you're willing to spend versus how accurate you want it to be for the diversity.
Of course, if you choose a step size more wisely, or if you apply some improvement of the step size, then of course you will get better accuracy or better convergence speed. But that's not our focus here. I mean, all the comparisons are done with the same method of choosing the step size. I mean, those differences only exist in the calculation of the direction. The step size is the same for every algorithm we compare here.
Any other questions? We still have time for a few questions.
So my question, same question but better worded. How many points are there in the Pareto front if you're only considering deterministic policies? Is it an exponential growth still?
I think so. I think it will grow with the size of the MDP. But whether it's exponential or not, we don't have a theory to prove that. But in our experiment, we do observe that when the scale, when the state action space grows, the Pareto front, the deterministic point on the Pareto front grows dramatically. But I would say, I think this is the least thing you have to do, right? If you want to precisely describe the Pareto front, you have to describe every point on it. So that's the least complexity.
I have a very intuitive question. Since your domain or the surface you consider is actually a polygon-like thing, right?
Yes.
So usually the solution would occur at the vertices, right? Or edges. You don't have to look at those points on those faces.
Oh, yes. I can, so the short answer is that we are considering an MDP, and we are talking about the stochastic solution. Stochastic solution means that when you talk about the policy, you have certain probability of doing one action, you have certain probability of doing the other action. So that means it's a mixture of different deterministic points, so then that can locate on the surface.
What's your answer?
So that I just explained why in my in that work, phases could be part of the Pareto front because it's a Pareto front of both the deterministic policies and stochastic policies.
All right, so interior point, good.
What?
An interior point of a face could also be,
Yes, could also be a Pareto front.
oh, really?
Yes.
All right, other questions? Now, I would like to remind you, our next talk will be given by Dr. Hank Dates next Wednesday. It's going to be an exciting talk as well, so, and also that, please sign in before you take the pizza.